Good morning and welcome to today's Physics and Astronomy Colloquium. A special thanks to today's speaker, who is David Brenner from Columbia University in New York City. David was brought up in Liverpool and he did his undergraduate degree in physics and philosophy at Oxford before gaining a master's in radiation physics from the University of London and a PhD from Surrey, in which he applied aspects of theoretical physics to studies of radiotherapy. After his PhD studies, David moved to a postdoc position at Los Alamos in the USA and then on to Columbia University in New York, where he's continued applying all aspects of physics to cancer treatments and radiation safety studies, making important contributions to recent events involving nuclear accidents and also testifying before the US Congress on radiation safety of airport scanning devices. David is currently the director of the Center for Radiological Research, which was founded at Columbia University about 100 years ago by one of Marie Curie's PhD students. This morning, David's going to talk to us about a different area of research, but still very much rooted in basic physics principles of light-matter interactions. Following on from the death of a close friend who caught a drug-resistant infection while in hospital, David began investigating whether a safe wavelength of ultraviolet light could be employed to prevent the airborne spread of viruses and hospital-acquired infections. He's been working on this with his team at Columbia for close to 10 years, but since the onset of the current pandemic, their research has gained worldwide attention. Now, David has woken up in the city that never sleeps to join us this morning. This isn't the first 5 a.m. call that I've been on with David, as just 2 weeks ago, just now, we were both presenting at a UK government innovation workshop, and we're pleased to say that the far ultraviolet C light our technology has been identified for government acceleration funding. So once again, thank you, David, for your early rise. We're very much looking forward to your presentation and talking with you afterwards.
Hey, well, thank you so much. It's a pleasure to be here, bright and early in the morning for me, in the morning for you. So if I could have the first slide, thank you. Yeah, so I'm going to talk about far UVC light, as you heard, and I'm going to talk about why it might be useful and the safety and efficacy aspects to it. So if I could have the next slide, please. Yeah, and apologies for rushing to the bottom line right at the beginning, just in case anybody needs to go. And really, the bottom line is we're all fed up with the need for social distancing. We're all fed up with having to wear our masks all the time, and we're all not really seeing when this is going to end. And our goal is really a safer resumption of just normal indoor activities, and we want to do that by creating an indoor space which is continuously cleansed. That's the general idea. So if I can have the next slide, please. So how can we efficiently kill airborne viruses in spaces where we are? Well, of course we already know how to kill every kind of bug, every kind of virus, every kind of bacteria, and that's with ultraviolet light. And I'm speaking to physicists, so you all know what ultraviolet light is. It's just a shorter wavelength of the electromagnetic spectrum right next to visible light and blue visible light. And the next slide, please. And we've known that UV light is really, or light is very good at killing bacteria and other organisms for a long time. This paper is 1878, talking about the effect of light on bacteria and other organisms. And the next slide, please. And by beginning of the 20th century, it was actually known what type of light is the most effective wavelengths, and it's UVC, UVC light. Next slide, please. And we know pretty well how it works. We know the mechanisms by which ultraviolet light inactivates cells. And that's essentially through creating pyrimidine dimers, which you can see a physicist's illustration of here, both for DNA and for RNA. But essentially, it's producing disruptions to the genome, which in turn make it much harder for the cell to correctly divide. And the next slide, please. Yeah, I'm not seeing the next slide.
No.
No, I'm still seeing the pyrimidine dimers here.
I can see it.
Oh yes, yeah. Now it's moved on. A slow move. Yeah, I'm one of the really nice advantages of ultraviolet light, and it's something that we're all concerned about right now. Is the issue of mutant viral variants. We're all worried about the British variant and the South African variant and the Brazilian variant. From the perspective of germicidal UV light, it's almost certain that they are going to inactivate these mutant variants equally effectively. Details of the spike proteins, for example, simply aren't going to affect how UV damages a virus. So that's a major plus for us. Okay, and if I could have the next slide. Okay, so the downside of conventional germicidal UV light, which is typically comes from mercury lamps at 254 nanometer wavelength, is that it has safety issues associated with it. It has safety issues in terms of the skin. It has safety issues in terms of the eye. So certainly in the past, or in the recent past, the major applications of germicidal UV light have been in situations like you see in front of you, where you don't see any people in these pictures. So it's used, for example, in my own hospital to decontaminate operating theaters overnight. Everybody leaves, you turn the lights on, and by the morning you have a nice clean room. And on the picture on the right is actually a New York City subway, which have also been decontaminated or are being decontaminated overnight with conventional germicidal 254 nanometer light. But again, no people present there because of the health and safety issues associated with conventional germicidal UV light, which is all very well and good. But if you look at that subway train, come 6 o'clock in the morning, when it goes back into service, very quickly it will become contaminated again. People cough and sneeze and talk. So what you'd really like is something where you're decontaminating on a continuous basis during the day in occupied spaces. Next slide, please. And so with conventional germicidal UV light, you basically have to go to some sort of indirect route. And there are several ways you can approach this, and with some success, I will say. Upper room germicidal UV is what's being illustrated here, where you don't expose the lower part of the room where people are present. You have the lights exposing the upper part of the room, and then you try and get circulation of the air from the lower part to the upper part, and the upper part to the lower part. So you're indirectly trying to cleanse the air around where you actually are. And the next slide, please. So another indirect route is putting a germicidal UV lamp inside the air conditioning, inside the HVAC system. Again, you're not directly decontaminating the air around where you are, which is what you'd really like to do. So next slide, please. So yeah, our goal and what we'd really like to be able to do is to find a wavelength that will kill airborne viruses, but still can be safely and continuously used in occupied locations. In other words, that's safe for us, but will still kill viruses. And that's what we're going to talk about today. So if you can click the next slide. So conventional UV, just to remind you, is to 254 nanometers. And we're going to talk about what's called far UVC, which is at roughly around 220, 222 nanometers. With a range, it could be anywhere in the range from about 210 to 230 nanometers. You might think, well, that's not very much difference, 220 versus 250, but if I can come to the next slide, you'll see actually that's quite a difference. So what's shown on this slide is actually the mean absorbance coefficient, how well the light gets absorbed by 8 common proteins. And actually, there's around 200 nanometers. There's a protein resonance. So all proteins absorb these lower wavelengths incredibly efficiently. You see the absorbance going up quite dramatically from 250 to 220. So what does that mean? What's the significance of the fact that you get more absorbance in protein at this 222 nanometer wavelength? So next slide, please. Well, what it means is that far UVC light, this 220 nanometer light, can really only penetrate very, very short distances in biological material. So, for example, if you look at the skin, and on the right you'll see roughly the structure of the skin. On the very surface of the skin is the stratum corneum, which are the dead cells that are being sloughed off from the epidermis. Below that is the epidermis and the dermis, where all the live cells live. So the far UVC light can really, if it's highly attenuated in the stratum corneum, the dead cells. So actually, very, very, very little of it can reach the epidermis or the basal cells at the base of the epidermis. And likewise in our eyes, on the surface, excuse me, on the surface of our cornea is the so-called tear layer. That's the very outer layer of our eye, and likewise that attenuates the far UVC light. So essentially, because the far UVC light has such a short range in biological material, it can't get to the key living cells, the basal cells of our epidermis or inside our cornea. On the other hand, viruses and bacteria are more than an order of magnitude smaller in scale compared with what we're seeing here. So far UVC light can certainly penetrate them and kill them. And that's the damage differential that referred to in this slide. That it's a matter of scale, that this far UVC light can't penetrate significantly into the living cells in our skin and in our eyes. On the other hand, microbes, bacteria and viruses are so much smaller that the far UVC light can penetrate and can kill them. So that's the basic biophysics behind far UVC. Next slide, please. So we really have only 2 questions that we need to ask, and but they're big questions. First of all, is it really safe? I've given you a biophysical argument that nobody's going to step inside a UV under a far UVC lamp based purely on biophysics, and does it work? Does it really decontaminate occupied airborne air spaces? So let's start with safety. Next slide, please. So there's 3 aspects, I think, to safety, and the first I've talked about, it's the biophysics. That's really what's driving everything. And the second aspect is actually there is an existing national, international safety regulatory framework right now as to how much UV light you and I can be exposed to in any given period of time. So people can't be exposed to any amount of light, and that framework's been around for decades, in fact. More recently, as people have been thinking about far UVC light, there actually have been many experimental safety studies, both at Columbia and elsewhere, and big star here to Scotland, to St Andrews and Dundee. Human skin models, human skin, mouse skin, mouse eyes, and I'll talk a little bit about all of those. Okay, next slide, please. Okay, so I've talked. I'll talk just a little bit about the regulatory framework. So, there in this country, in the US, there is an agency called the ACGIH, American Council for Germicidal Industrial Hygienists. I think probably got that wrong. And they produce graphs like this one on the left, a so-called TLV, threshold level values, which is basically how many millijoules per centimeter squared people can be exposed to per, in this case, 8 hours. And there is also a corresponding international agency, and the UK will fall under that. But by an extraordinary coincidence, their levels, their TLV levels, are exactly the same. So they work together. So right now, the regulation is at 222 nanometers, you can't be exposed to more than 23 millijoules per centimeter squared per 8-hour period. That said, really because of all the safety studies that have gone on in the last couple of years, the ACGIH has just announced, and they published this, a notice of intent to change their threshold level values, and by a lot actually, by 18-fold for the skin and 5-fold for the eye. To me, it's a bit odd you'd have different regulatory levels for different organs. So I think in practice, it's going to be the eye value that's going to control things. So this 23 millijoules per centimeter squared per 8 hours is probably going to go up to 100 millijoules per centimeter squared per 8 hours in the next year or so. The next slide, please. Yeah, so I mentioned there have been lots of published safety studies at 222 nanometers. And yeah, certainly not all in this picture. I kind of lost energy at some point, popping in all the new safety studies. But if I can go to the next slide, I would say that essentially all of them, bar one, indicate safety, even at much higher doses than those threshold level values. And an issue that I'll return to a little bit later is the actual spectrum of light that we're talking about. So I've been mentioning 222 nanometer light in terms of far UVC. So why am I talking about 222 nanometers in particular? It's because those are the most practical lamps today to generate far UVC light. And they're so-called excimer lamps, and they're krypton chlorine excimer lamps. So it's a gas mixture of krypton and chlorine. And that when you put a voltage across it, like moves into an excited state, a so-called excimer. And that de-excites with a series of monoenergetic lines, by far the most frequent of which is the 222 nanometer line. So you see in these spectra here a peak at 222 nanometers, and that's what we'd like to see. The excimer lamps, however, do have other de-excitation modes, and the krypton chloride excimer de-excites with other wavelengths, and the excited chlorine atom too, or chlorine molecule, I should say. So what one needs to do is, as you see, these are starting to get into the 250 nanometer range, where we know that we don't have the safety associated with 220 nanometers. So we have to filter out these longer wavelength contaminants. And you see the two lower curves here have filters in place. And this is a log scale on the y-axis. So that's actually a significant amount of filtering. So the lamps that one would use, or one is using in practice, are actually filtered krypton chloride eczema lamps. And if I can have the next slide, I'll show a little bit of the significance of that. So here are two papers, one on human skin safety with a lamp which doesn't have a filter, and one with human skin safety with essentially the same lamp but with a filter. And they're both looking at the same thing. The first one on the left is again, they're both looking at erythema, essentially a sunburn, in human skin in healthy volunteers. And the conclusion on the left, in the lamp without the filter, at low doses, the source was capable of producing both erythema and CPD, which is a type of DNA damage in human skin. It's basically the same study on the right here was done actually with the same sort of lamp, but with a filter. And what they saw was they did not see any DNA damage or any erythema. And all the other studies, bar the one you see on the left, have been safety studies, have been done with lamps with filters. And essentially, there has been no evidence of safety issues, certainly at realistic doses within what you might realistically be using in practice. Next slide, please. Our own safety studies at Columbia have involved really two models. One, a ex vivo human skin model, and that you see on the top left here. Basically, people grow human skin, and these models are really developed for the burns world, for skin transplantation. But you can basically develop a model which recapitulates all the processes of human skin. So this picture here has a stratum corneum, has an epidermis, has a dermis. So it's a simple or practical ex vivo model. And the graphs you see on the left are looking at the amount of DNA damage. These are two types of DNA damage, CPD and 6,4-PP, as a function of the UV fluence, both for a conventional germicidal UV lamp, which is the orange, and for far UVC light, which is the blue. And what you see is that there is far less damage with the far UVC light, and that's because the far UVC light can't reach the epidermis. It's absorbed in the stratum corneum. So if it physically can't reach the epidermis, obviously it won't be producing DNA damage. The type of safety study that you see on the right is an in vivo study, and we use hairless mice. So these are not genetically modified mice. These are simply mice which don't have any hair. And we've essentially just finished a 60-week exposure safety study where 100 of these mice have been exposed 8 hours a day, 5 days a week to different doses of far UVC light. And if I can have the next slide, please. Yeah, just a little bit more detail on that study, because it's finished, but we haven't actually finished the analysis yet. So we used commercial 222 eczema lamps. We had 96 mice given daily exposures of either 500, 250, or 125 millijoules per centimeter squared, 8 hours a day, 5 days a week for just over a year. And over that year, every week or two, they had regular skin tests and eye tests. The exposures are now finished. And now we've made slides of the skin and made slides of the eye, and also done various functional tests. And we're in the midst of examining all those many slides to see if there's any abnormal pathology. But I will say, up to this point, we have not seen anything. the most recent set of studies, the DNA damage, is a blinded study, so we don't know what doses correspond to what slide, so can't make any statements about that. But the studies that were done during the exposure, we didn't see any health issues whatsoever. Next slide, please. So, of course, you might argue, well, those are mice, and we're not mice. Are they in any way a realistic model for in terms of safety for humans? And I would argue yes. And the reason is that in the key to the safety of far UVC light, as we've talked about, is the stratum corneum and the tear layer, which are essentially attenuating the far UVC light. So the question becomes, is the thickness of the stratum corneum and is the thickness of the tear layer similar in mice and humans? And if you look at this table here, these are actually averaged over several studies. I think you'd say the answer is yes. And in fact, the human stratum corneum is actually much thicker than the mouse stratum corneum. So the mouse is going to be a pretty conservative model. So I think the mouse in general is a good model for far UVC safety for people. Next slide, please. Yeah, well, what about the good bugs? So the microbiome, of course, is incredibly important for our health and welfare. Most microbiomes, of course, are inside the body. The one we think about most is the gut microbiome. But of course, far UVC light can't remotely reach the gut microbiome, and so won't affect that. So the only relevant microbiome is actually the skin microbiome, which is right on the surface, is families of bacteria that live on the very surface of our skin. And if I can have the next slide. Yeah, so right on the surface of our skin, here's a conformal laser scanning image of the microbiome, the orange part here. Our skin microbiome has a really tough life. So everybody in the middle of the left-hand picture, and flowed in front of a UV lamp, and I've sort of angled the UV light towards the camera just so you can see it, but that would normally be aimed at the window there. And then at the far side, we pick up the viruses, and there are various techniques we can use to measure what proportion of those are alive and what proportion of those are dead. And for those in the technical world, the TCID 50 technique is the standard technique that we use. And what you see on the right is the results of our paper from last year on using aerosolized coronaviruses. And you see that at the pretty low doses, a few millijoules per centimeter squared, you get significant cell killing or inactivation. And you see one, two, three, 4 orders of magnitude, at least 4 logs of killing, typically at very low doses. And again, just to remind you, the sorts of doses that would be thinking of giving in the real life are the 8-hour limit right now is 23 millijoules per centimeter squared, and the proposal is to move it up to 100. So we think we are in the right ballpark for a significant amount of reduction of the level of these viruses in the air. So H229E and OC43 are labels for these 2 graphs here. What are they? Well, they are coronaviruses, and they are common coronaviruses. So that they're not the SARS-CoV-2 coronavirus, because it's very hard to do those studies. You need a whole different level of safety. So these are surrogate coronaviruses, if you will. And I'll talk about evidence that these basically respond the same as the SARS-CoV-2 virus. But basically, from a practical point of view, these are much easier to use. Next slide, please. Yeah, so this is the paper from last year. Far UVC light, 222 nanometer, efficiently and safely inactivates airborne human coronaviruses. And basically, based on these numbers, we made the claim in a very simplistic way that at the current regulatory limit of 3 millijoules per centimeter squared per 1 hour, you would get 90% viral inactivation in 8 minutes, 95% in 11 minutes, 99% in 16 minutes. And if you did increase the regulatory exposure limit by a factor of 4, you'd just decrease these times by about a factor of 4. But I'll talk more about the practical implications as we go on. Okay, next slide, please. Yeah, so these studies were done with what I call seasonal coronaviruses, and those are coronaviruses which probably most of you have suffered from at some point in the past. It's basically those are what we call getting a cold when you get infected with these viruses. On surfaces where we actually can do some SARS-CoV-2 studies, the 222 nanometer inactivation in these seasonal coronaviruses is pretty similar to the surface inactivation with the SARS-CoV-2 virus. So we have some evidence that these are going to respond the same, these different human coronaviruses. And again, we actually expect that because it's really the genomic size which counts, which is going to be dominating the inactivation. And they're the same for all the human coronaviruses. Next slide, please. Okay, so here's my bottom line slide again. Again, we really want to get away as much as we can from social distancing and mask wearing in the future. And far UVC light potentially does allow a safer resumption of our normal indoor activities, simply because we're going to be continuously decontaminating the air in which we're actually in at that particular moment. Next slide, please. So now obviously we've talked about mostly about coronaviruses, but in a sense, this is a much more general approach to reducing viral contamination in the air, because the UV light doesn't really care so much about the details of the virus or the bacteria. It's really damaging primarily the DNA and the RNA, and a little bit damaging the protein too. So would it work for mediating other airborne mediated diseases like the flu, like measles, like TB, and the next pandemic, which dare I say it, will come one day in our lifetimes? And I think the answer is probably yes. What you see here is the corresponding data that I showed you before. There I was we were inactivating human coronaviruses. Here we're inactivating the H1N1 influenza virus, and with very similar efficiency. So you might imagine if these lights are indeed widely installed, they could take a bite out of our seasonal influenza epidemics that we have every year. Next slide, please. So let me, my last few minutes, talk about where we're going on ongoing developments, both ourselves and other folks around the world. One of the most important aspects is to really understand the wavelength-specific risks. So this is the ACGIH TLV that I showed before, basically the amount of light that you're allowed at any given wavelength. And what you see is it's pretty low. it's pretty low in the 220s. Sorry, pretty high in the 220s. You're allowed more light exposure in the 220s than you are in the 250s. But obviously it's not as simple as that. It's not 220 is perfectly safe and 250 is perfectly unsafe. So there's obviously some gradation in between. So we'd really like to understand the wavelength specific risks. And that's also in the context of the fact that these 222 nanometer lamps that we're using don't emit at a single wavelength. They're dominantly at 222, but they emit some higher wavelengths too. And we really want to know, well, how much filtering do we really need to get rid of the higher wavelengths? So next slide, please. I'm still seeing the same slide here. Can we move to the next one? Yeah, good. So the way we're doing that is to try and do some irradiations with single wavelength, or essentially single wavelength light. And for that, we've got a very intense broad spectrum xenon light source that you see on the left, and a monochromator that you see on the right, which basically takes that broad spectrum of light and produces very highly monochromatic single wavelength, quasi-single wavelength light. And the next slide, please. Yeah, and you see the spectrum here that produced by this system. So on the left, this is, I'm not sure my eyesight is up to this. That's a spectrum at 204 or something, I believe, on the left, and that's the sort of width of the monochromatic spectrum we can get. We can get depending on the size of slits we use, we can have a 2 nanometer full width half max, or 4 nanometer full width at half max. And on the right, you see all the spectra we're planning to investigate. So basically, we're trying to do it wavelength by wavelength. The next slide, please. Yeah, and the systems, the safety systems we're going to use for that, I've referred to before, the artificial human skin systems, and actually they're available commercially. I mean, we in our earlier work we grew these from scratch from single cells, but actually it's much easier to buy these 3D skin tissue systems. And the company Matec has a nice model epiderm for human skin, you see on the left, and also has a model for the cornea, epiocular. And so those are the systems we're going to use, and we're going to measure DNA, going to expose them to these single wavelengths, and then measure DNA damage. The epiocular that you see on the left here, an issue there is that it doesn't have the tear layer built into it. The epiderm does have the stratum corneum, the dead cell layer built into that, but the epiocular we would have to add our own tear layer. If I can have the next slide, please. Yeah, and interestingly, very recently, a new product has hit the market, Cationorm, which basically is a very realistic model for the tear layer. And it's being used like liquid tears in practice, but we're going to just put little drops of it on top of our epiocular model. Next slide, please. And of course, we're not going to do these, but I know in Scotland, you are going to be doing these sorts of studies. We need more safety studies actually in living humans. Next slide, please. So the future developments of far UVC light that I think are going to happen, I've grouped into three groups here: simulations, some demonstration projects, and then real-world installations. Next slide, please. In terms of simulations, so the paper that we published was basically exposing airborne coronaviruses in a controlled laboratory chamber and drawing conclusions from that. But of course, in the real world, the microbes are floating around in real live rooms. So if you really want to understand what's going on in the real world, a good way is simulation. So CFD, computational fluid dynamics simulations in real life, realistic rooms that you can then integrate with the UV transport and put in the inactivation data that, for example, that we produced. I think that's one very good approach to starting to see, well, what is the effect going to be in a real life room. And I know that the St Andrews Dundee team are actually working on some very realistic models here. Next slide, please. Yeah, demonstration projects. We like to demonstrate efficacy in real life rooms. And one very exciting development is that we're probably going to be doing some studies at Leeds University in their so-called negative pressure aerobiology chamber, which is basically a small room of about 3 meters by 3 meters by 3 meters room. But it has negative pressure, so you can actually put microbes or airborne microbes in this room, and it's got an inlet and an outlet, and actually do measurements on inactivation. And we're certainly very much hoping that we'll get to do these sorts of studies in collaboration with our colleagues in Scotland actually very soon. Next slide, please. And then in terms of demonstration projects, efficacy measurements in real life rooms is a potentially important step too. And we actually are planning to do some studies actually in some Taco Bell locations. I trust you have Taco Bells in Scotland. Yeah, actually, sort of my favorite tacos, sort of. The issues are different in a real life room as opposed to an artificial chamber like the Leeds facility, because you can't start blowing microbes around in the air, certainly in this day and age. Typically, when you want to use a safe surrogate, you use a phage, you use bacteriophage as a surrogate for whatever virus you're interested in. But in this day and age where we're so concerned about airborne viruses, nobody is going to let you do even that. So I think what realistically we are going to end up doing is looking at the natural level, the in situ background level of viruses in the air without a lamp, and then turning the lamps on and then seeing how that background level of viruses changes. So we're not actually introducing any viruses into the environment, even the safe viruses. And so we've been doing right now some background measurements of, well, what viruses are actually present in natural indoor air. And what we're finding is that doing the studies now, where we're all masked up and being very careful and lots of ventilation, we're seeing less background viruses than we would have a year ago. So we do see the H1N1 influenza virus, but not as commonly as, for example, last year. And I think we know that because we're in what would normally be flu season, and there really hasn't been much of a flu season. And I think one can attribute that to the fact that we're much more careful about blowing our viruses around. We might wear masks and so on. But I think that is still the only option that we have to do some measurements actually in a real life situation, in a Taco Bell situation, and we're almost certainly going to do that. Next slide, please. Yeah, and then there's real world installations, and actually in this country, in the US and in Japan too, these have been installed quite a bit, and the rate of installation is increasing quite rapidly at the moment. I show you just three examples here. The one on the left is a coffee bar down in New York City in Greenwich Village. And we actually went down to this coffee bar and we took lots of measurements and so on. The one in the middle, this is the so-called Seattle Space Needle. The dominant feature of the skyline in Seattle is this very thin, large building, the Space Needle. Lots of elevators going up and down, and they've all got Phi UVC installed in them. And elevators, of course, is a really good application for Phi UVC, I think. And on the right, I don't know if any of you follow American football, but one of the American football teams is the Miami Dolphins, and all their training rooms and some of their other rooms too have been fitted with Phi UVC light. So it's starting to be used in the real world, I think, but always, of course, keeping with the current regulatory limits. Next slide, please. I think we're coming to the end here. So yeah, looking ahead, where might Phi UVC light be used, and how might it be used? Well, basically, it's always going to essentially be in the ceiling. It's going to be, and that could be retrofitting the current lights in the ceiling to a combined Phi UVC visible light fitting, or they can be simply extra Phi UVC light fittings. And that's basically going to be useful in any situation where people are coming closer together. And see a big list here of these are just places where people come together a lot. All these places, in principle, could benefit with Phi UVC light. And I think my final slide, I think, is the next one. Yeah, and again, just to re-emphasize the fact that this solution is different from for example, a vaccination solution. So a vaccine is very specific to one virus, and as we're starting to learn, even one variant of one virus. And if you have a different virus, you have to have a different vaccine. Phi UVC light is much more one size fits all than that. But hopefully it's going to be useful both for influenza epidemics, for reducing measles and TB in schools, and for the next pandemic, which we hope won't happen, probably will happen. So I think my time is up. I'm going to stop, and not sure how we're dealing with questions, but I'm very happy to answer questions.
Well, thank you. I think we try and give a round of applause if anyone can unmute their mics. Thank you to David.
Thank you.
David's camera isn't actually functioning just now. Can you advise on that, Damali?
Okay, I can see me. I'm still here, though. You don't have to see my visage necessarily.
Okay. Well, we've got a few minutes now for questions, and
yeah, could you moderate? Could you moderate?
Sure. I can try and do that, David. Yes. Just before we start, I want to say that David's mother is a graduate of the University of Leeds, and David told me yesterday that his mum, who's in Liverpool just now, is thrilled that our son is going to be working with people from the University of Leeds for their bioaerosol chamber. So that was a nice story that came about yesterday. Now, I see there's a couple of questions that came up in the chat box, and I'll just read those out to you, David. So there was one about people that have very fair skin or babies. Would they be adversely affected or scared of ultraviolet light? And then the second question was, would this ultraviolet light damage other materials, plastics, or anything else that's not just our skin, but materials around our home?
Well, let me start with the first question. I mean, are there going to be sensitive subpopulations that are more sensitive to far UVC than average? So what that boils down to is the question of, well, is the stratum corneum and is the tear layer different in different populations? And the answer is basically no. The stratum corneum, even in infants, is about the same thickness as our stratum corneum. Doesn't change very much. Doesn't change with skin type, for example. So dark skin, light skin. The stratum corneum is still about the same thickness. And even people who have so-called sensitive skin, again, the stratum corneum is not affected. So yes, of course, people's skin is different, but in terms of their living cells. But if the light can't reach those living cells because it's blocked in the stratum corneum, then you're still going to have that same level of safety. So I think I don't think there's going to be an issue with different subpopulations, and I will say even people with dry eye, they still have a level of tear layer on average, which is pretty similar to the average in people who don't have dry eye. Now there was a second question which I've already forgotten.
Okay, David, the second question was about the effect of UV on household materials.
Yeah, well, again, because it's not very penetrating, it's not going to have any major effects. I must add, it's not really my area, but one group that's thinking about using far UVC and is worried about that is Boeing. So they're interested in installing it in their aeroplanes, and of course they're very worried or very concerned that they don't want their nice fancy seats and whatever to be damaged. So they're involved with a lot of long-term studies of materials damage. I can only say that if it was me and I had a choice between some damage to my chair and not getting COVID-19, I know what I would choose. But yeah, I mean, it is an issue, and it's not an issue that I know too much about. But it's not. I mean, it's clear that there are not major issues. I'll give you an example. The plastic around that housed our mice in that 60-week fairly high dose study, that wasn't affected at all by the far UVC light.
Okay, another question, I like this one. How energy hungry are the far UVC lamps? So would businesses be able to afford to install them from a cost perspective and from an energy consumption perspective?
Well, from an energy consumption perspective, it's not much of an issue. They don't take up much more power than conventional lighting. In terms of the capital outlay for these lights, that's much more of an issue. Because this is a very new technology. The lamps right now are relatively expensive. So I've seen some in the $500 range. I've seen them in the $1,000 range. So that is going to be a significant issue in terms of future deployment. And in something I hadn't talked about, in the long term, you would expect that we will be moving from gas-based lamps to solid-state lamps, just in the same way that in our lighting, we've moved from filament-based lamps to LEDs. You would expect that same move in the far UVC world. Now, far UVC LEDs aren't there yet. The technology is not quite there to produce the intensity of lamp that you would like. So in our lab, we have some far UVC LEDs, and they work, and we have all the same issues and questions as we have for excimer lamps, but the intensity isn't there at the moment. So lamp development, I think, is really what is the key to the future of far UVC light. One issue in terms of the price right now is as they start to sell large numbers, the price goes down a lot. So I was reading about the history of the cost of conventional filament lights in the turn of the last century. They started off very expensive, but as people started to buy lots and lots of light bulbs, the price went down by 2 orders of magnitude pretty rapidly. Not sure I expect the price of UVC lights to go down by 2 orders of magnitude, but I can certainly expect that it might go down by 1 order of magnitude, and then it becomes very much more affordable, I think.
Okay, I think that discussion about other light sources has answered one of the questions that has popped up in the chat, so I'll skip over that one. Someone's asked another consideration, maybe people that have had their cataracts removed. Is that an issue?
Yeah, well, no, I mean, you still, your cornea is still present and the tear layer is still present. So no, I don't think it would be an issue.
Okay.
But let me go back to the issue of light. So I'm talking to a physics audience here. So let me throw out a challenge to this physics audience. I mean, we need new ideas for how to produce far UVC lights cheaply and efficiently. And we need to think outside the box of different approaches to producing light in the 200 to 230 nanometer range. And people are constantly sending me ideas, most of which are not practical ideas, but I think it's the physics and the engineering communities that are hopefully will step up to the plate and produce new ideas.
Okay, another question, David, was you mentioned about the time to inactivate the virus by 90% was about 8 to 10 minutes or so. And how practical are the lights going to be in an environment where someone is coughing or someone is actively shedding virus particles?
Well, first of all, those times are very dependent on the details of the lights and the details of the room. And the sorts of computational fluid dynamics simulations that are going on are really going to give a much better estimate of those. But the issue is, well, let me go back to if you and I are standing in a room and I sneeze right in front of you, no light is going to help you there. Because what is going to come out of that sneeze is a whole variety of different sizes of droplets and aerosols, and those larger droplets are going to hit your face if you don't have a mask on, and we're standing very close to each other. And far UVC light certainly won't help in that regard. But at the same time, lots of smaller aerosols are being produced. The larger ones will, within a few seconds, will actually fall to the ground. So other than standing right in your face, that's not a sort of immediate issue. The smaller ones are not affected by gravity so much. They won't fall to the ground. They're actually going to start circulating within that room, depending on the airflows. And that's really what we're targeting. We want to reduce the ambient levels of virus within that room. So the more rapidly you can do that, the better. But we don't need to do it within the time frame of a few seconds, because we never will be able to do much reduction in the time frame of a few seconds. We're looking ultimately, I hope, for time frames of a few minutes. So we're trying to reduce the ambient levels of virus in the air over a time frame of minutes.
Okay, I'll maybe take 1 or 2 more questions, because I'm aware that we're going to have a separate breakout room to meet with David in a few minutes' time. But there's another question that's come in from Rob. How stable are the outputs of these sources over time? Does the output of the UVC decrease over time? Are the bulbs, do they wear out? Can you just talk about the lifetime of bulbs at present, David, not the future?
Well, they do have a lifetime, and they will have to be replaced. Their lifetimes are typically a few thousand hours, as best I understand it. And I think they very slowly decrease their output over that time, and then towards the end of their lifetime, they start to decrease actually fairly markedly. Again, future lamps hopefully will be different and will be improved from that. But yeah, lifetime, in the issue of lifetime, the issues of intensity are key to the actual technology of the lamp.
Okay, I think that's no other questions are popping into the chat just now. So we'll maybe end this session and take a break of a few minutes. And those of you that would like to join to talk with David in another session, just click on the link that was sent for that. But if we can maybe all unmute our mics and give David a nice Scottish warm welcome round of applause.